All right, folks. So yeah, I'm just going to repeat what I just said there because I was a few minutes late hitting record. Um, so basically what we're looking at here is complex reactions, which is a reaction that takes place as the result of a sequence of elementary steps. And we're using this reaction here as an example where we have C4H9Br plus Cn minus reacting to make C4H9Cn plus Br. And we know through experimental study, actually the person who discovered this reaction goes by the name of, his name is Christopher Ingold, who's perhaps one of the most accomplished chemists of all time who never got a Nobel Prize. He had enemies on the Nobel Prize Committee. His son actually moved to Canada and is one of the top chemists in Canada right now. Anyway, this reaction has an initial first step, step one, first elementary step, which is unimolecular. It's unimolecular because there's a single molecule right over here that's reacting. It's not reacting with anything else. It's just reacting all on its own, and it splits in half. We say this is a first order reaction, unimolecular reaction. Then there's a second step where this cation that is a product of the first step is a reactant in the second step. That cation then reacts with cyanide to make C4H9. So when you have a complex reaction that is a sequence of steps like this one, if you add all these steps together, so basically we're adding step one plus step two, and you cancel what appears on both sides, right? So if you look at this, we see this cation appears on the right and it appears on the left over here. So when it appears on both sides, you cancel it, and the sum should be equal to the overall reaction. Okay. We have names for all these different things. You know, the products of the things that are on the product side, reactants are on the reactant side. Something that is formed in an early step and then consumed later on, like this cation, is formed right at that in that step one, and then it's consumed in step two. We call those things intermediates. We'll be looking at that in a bit more detail. Okay, so we have these two steps. We have a first order step and we have a second order step. What's the order of the overall reaction? Turns out you actually can't tell. You don't know. There's no way to really predict what's going to be the order of the overall reaction without really doing experiments. We're going to see that in a little bit, what those experiments might look like. You certainly can't get the order either from the overall balanced equation. So here's another one. You can't get the rate law from the overall balanced equation. You can for elementary steps. If you have an elementary step that's A plus B goes to C, we know the rate is going to be equal to K times the concentration of A times the concentration of B. Only for elementary steps. But not for complex reactions, not if there's multiple steps. So take a look at this particular reaction. Okay, we have S2O8 2 minus, is that thiosulfate anion? Then we have 2I minus goes to 2 sulfates plus I2, everything's aqueous, it's all done in aqueous solution. Experimentally, the rate law here was found to be this. This is second order because it's first order in S2O8 2 minus and first order in iodide. 1 plus 1 is 2. So we say this is second order, and this was determined experimentally. Notice that these exponents do not match the coefficients in the balanced reaction. There's a 1 here, and that sure matches, but there's a 2 in front of the iodide, which is not the same as the exponent. So we can tell that you can't just look at the balanced overall reaction and get the rate law that way for complex reactions. Also, complex reactions sometimes have exponents that are weird numbers. So here's an example. If we have H2 plus Br2, both in the gas phase to give 2HBr gas, this actually gives a rate law, which looks like this, where, we have a 1 here. If there's a 1 there, we don't write it in. But it's first order in H2, and it's like a half order in Br2. So sometimes you have these mechanisms that are pretty complex. They involve equilibrium steps, and you can have experimental rate laws that have pretty unusual exponents in there. So the order of this overall reaction is 1.5. And you can basically have any number decimal fraction as your order for the reaction. Okay, so what we want to do then is figure out for a complex reaction how we experimentally determine the rate law. And it actually turns out there's lots of different methods you can use, but we're going to deal with one such method of doing this. And this will be looking at what we're going to be doing is running a series of experiments where we set the concentrations of all the reactants to some specific known value, and then we let the reaction take place. We follow the loss of one of the reactants or the formation of one of the products, and we express the rate of the reaction in terms of that concentration, like we did at the beginning of this chapter. So here's an example. We're going to do a reaction where we're starting with N2O5, and it's going to react to give products. One of these red lines would be what you'd expect to see for the concentration of N2O5 at some given starting concentration. So if we start a concentration of N2O5 at that value, whatever that number is, when the reaction takes place, N2O5 starts to react away to make products, and it follows this red line where the concentration of the reactant falls in an exponential fashion. Right? This is what we see very often for many types of reactions. But at the initial time, right, at time equals 0, the tangent to that curve, which is this black line, will have a slope equal to the rate. And then the reaction slows down as the reaction proceeds. The slope gets flatter, and it slows down because you don't have as much reactant to be undergoing reaction. So in terms of moles per minute or second, the reaction is going to slow down. But at time equals 0, what we say is the slope of that tangent line, we call that slope the initial rate. So later on, like say down here, yeah, the rate's going to be something different because our concentration is something different, and the reaction's like half over. But what we're concerned about is the rate at time equals 0, the initial rate, because that's the only time where we exactly know what the concentration of the reactant is, because we decided what that was going to be. We do another experiment where we're going to have a different starting concentration and a different initial rate. You could have a third, fourth, and a fifth experiment where we have different starting concentrations and different initial rates. So what we expect to get here is basically a table of initial rates and concentrations. So let's develop one of these tables and show how we can use that to determine a rate law. Here is an overall reaction where we have lots of things going on. We have bromate. We have 5 bromides reacting with 6 H+ to give us a couple of products. We don't care what the products are generally when we're determining these mechanisms. Just a reminder, you cannot say the rate is just the starting materials raised to the exponents of the coefficients, because this is a complex reaction. Only for elementary reactions is that possible. So yeah, this would be a crazy order. If this was an actual chemical rate law, that would be like 12th order, which you basically never see. Maybe in the core of the sun or something like that, there's some reaction that's like this, but not on Earth. Okay, so here's what we're going to do. This is the reaction. We know the rate law is going to be rate equals K times concentration of the first reactant raised to some exponent A, multiplied by the concentration of the second reactant raised to some exponent B, raised to the multiplied by the concentration of the third reactant raised to the exponent C. So we know this is going to be true every time you have a chemical reaction. That rate will be the rate with, of course, different reactants put in there. What we don't know are what A, B, and C are. That's the part that needs to be experimentally determined. Okay, so what we're going to do then is just what we said we were going to do before. We're going to start with a bunch of initial concentrations. And how about just for the hell of it, for experiment 1, we're going to make the concentration of all 3 reactants 0.1 molar. And then what we do is we measure the initial rate. So that's kind of like over here. We have known concentrations of starting materials. We pick time 0, we watch something disappear, and we take the tangent, and we figure out the initial rate. And it turns out the initial rate under those conditions where everything is 0.1 molar is 1.2 times 10 to the minus 3 molarity per second, or moles per liter per second. Great, okay. Next, what we want to do is repeat this, and what we want to do is choose a second experiment where we change the concentrations. And the simplest way to do this is leave the concentrations the same for 2 of the species and only change it for 1. So we're only changing 1 parameter at a time. So for experiment 2, what you can see is all the numbers for concentrations are the same as experiment 1, except we're going to double just one of them. And what happens when we double them? Well, we notice the rate doubles as well. So clearly A, A is going to be some number. The concentration of bromate actually does, as we can see, have an impact on the rate of the reaction. So we want to do the same thing for all 3 of the reactants. We want to leave the other 2 the same and change only the one that we're interested in looking at. So if we go from 1 to 3, what you can see is, I guess I have it on the next page, going from 1 to 3, you can see that if you triple the concentration of Br minus and leave everything else the same, we end up tripling the rate as well. So it turns out that if you double a concentration and the rate doubles, or you triple the concentration and the rate triples, if they have that that relationship where they both increase at the exact same rate or the same factor, then that means the exponent is going to be 1. So because in the first case, when we're looking at changing BrO3 minus, double the concentration of BrO3 minus, you double the rate, that means the exponent here is going to be equal to 1. Same thing when you go experiment 1, experiment 3, we're going to triple the concentration of bromide while the others are left constant. We triple the rate, that means there's going to be a 1 here as well. So this is how we go about determining what the rate, what the exponents are for each of the reactants. We need to do these experiments. Last, you can see between experiment 2 and experiment 4, the concentration of bromate has been kept constant, the concentration of bromide has been kept constant, but the concentration of H plus has been doubled. And what we see is when we double the concentration of H plus, the rate has increased by a factor of 4, which is equal to a factor of 2 squared. So what that means is that the exponent is going to be a 2. And so you can see we have determined the last exponent in our rate law, which is going to be equal to 2. So what would you say the order of this reaction is? We have a 1, we have a 1, and we have a 2. 1 plus 1 plus 2 equals 4. We'd say this has a fourth order rate law. Now, as I said, you can sometimes do these by inspection. If you increase the rate of something, increase the concentration of something and the rate doesn't change, then the exponent is going to be 0. If you double the concentration of something and that doubles the rate, the exponent will be 1. And if you double the concentration of something and the exponent increases by a factor of 4, then the exponent is going to be equal to 2. That's by far the most common case. It's going to be one of those three things. But as I said before, sometimes you have these weird cases. So what you can actually do if you want to determine what the exponent is, so the exponent is going to be equal to the natural log of rate 1 over rate 2 divided by the natural log of concentration 1 over concentration 2. So if we were to look at an example here, if we were to compare 2 and 4, remember these were the ones where this and this were constant, this and this were constant, but we increased H plus by a factor of 2. And what we saw was the rate increased by a factor of 4. We can take those numbers, this concentration and this concentration, this rate, and plug it into this equation where we would say natural log rate 1 is 2.4 times 10 to the minus 3 over rate 2, which is 9.6 times 10 to the minus 3 over natural log of concentration 1, 0.1 molar over 0.2 molar, and solve it that way, and that'll give you the exponent as well. So there's multiple ways you can consider doing this. Whichever way you find makes more sense. Certainly it's faster if you can just look at them and say, oh, if it doubles and doubles, exponent's 1. But if you feel better, or if you have cases where the exponent is a number like 1.5, this is perhaps a better way to go about it. All right, let's do an example. We have CO plus Cl2 goes to COCl2. Everything's in the gas phase here. So what we can say right out of the gate is that the rate of this reaction will be equal to K times concentration of CO raised to the power A. We don't know what the exponent is yet. Could be 0, in which case CO does not contribute to the rate law. Times concentration of Cl2 to the D. And we don't care about the product. Looking at the reactants. So what we want to do is find a pair where the concentration of CO changes and not Cl2. And then what we want to do is have a second pair of experiments where Cl2 changes and not CO. So if you look at, let's say, we call these experiments 1, 2, and 3. If you look at experiments 2 and 3, what we see there is that the Cl concentration is constant, held the same. The starting concentrations are identical, but the concentrations of CO increase by a factor of 2. If you look over here at the rate has also increased by a factor of 2 when we doubled the concentration of CO. That means the exponent on CO is going to be equal to 1. Okay, so what we can do over here is scratch out A and put 1. Next, what we want to do is do the same thing for B, for Cl2. So we need to find 2 experiments where Cl2 changes, but not CO. And that would be experiments 1 and 2. These remain constant, but this doubles. And what we see is that the rate goes from 0.696 to 1.97. And if you look at that, that's not a doubling, and it's not a quadrupling either. So this is maybe a case where it's not so straightforward, and we want to use that equation. Okay. So remember, our equation just on the previous slide is this to determine the exponent. So for B here, the exponent for Cl2, it's going to be equal to the natural log of rate 1 over rate 2, which is 0.696 over 1.97 over the natural log of concentration 1 over concentration 2. And this turns out to give us the number 1.5, which, good thing we use the equation because that's a weird number, right? Normally it's 1, 2, or 0, but if it's some other number like this equation helps us get to there very quickly. So what that means is that our rate then is going to be equal to K times CO, and because the exponent's 1, we don't write it in, Cl2 1.5. So what's the order of this reaction? Anyone want to put that in the chat? There we go. Thanks, Adrian. 2.5. Okay. Notice that we're not quite done yet, though. The question says, find the rate law, including K, for the following reaction. We don't know what K is yet. So to find K, what we're going to do is take any line of data from the table, plug it into our equation, and solve for K. So what we can say then is if we rearrange this equation, K equals rate divided by CO, Cl2 to the 1.5. So we can pick any one of these 3 experiments. It doesn't matter which, all 3 will work. We'll take our rate, 0.696 molarity per second, divided by, concentration of CO in experiment 1 is 0.25 molar, times Cl2, which is 0.40 molar, raised to the 1.5. And if you solve that, what do you get? You get 11.0 molarity to the negative 1.5 seconds to the minus 1. So this is our value of K. Great. And so that means that our overall rate, our final answer to this question, should be equal to 11.0 molarity to the minus 1.5 seconds to the minus 1 times the concentration of CO times the concentration of Cl2 to the 1.5. Great. So that is how you go from taking this table of experimental data to determining what the rate law is for that reaction. So that's important because it explains how quickly things happen. This is particularly a hot area of atmospheric rate laws and determining rates for atmospheric reactions back in the 1990s when it was the 1990s when ozone depletion was taking place, and people were very curious about how quickly these atmospheric reactions were taking place to destroy ozone and what we might be able to do to prevent that from happening. And Nobel Prize went to a couple of chemists who were kinetic specialists and determined what was actually destroying the ozone layer. And we got rid of those products, and now the ozone layer is healing. So we're good, hopefully, as long as we can keep not making it. Okay, so that's where we're at now. What we would like to do is we're going to kind of transition into the next phase of this chapter. And what this phase of the chapter does is looks at what we call integrated rate laws. This is basically taking what we know so far about rate laws for chemical reactions and doing a bit of calculus to them so that we can put them in a form that is actually much more valuable to us. They allow us to learn things about reactions that are beyond what we can do so far. So far, what we can do is we can describe what the rate of a reaction is going to be in terms of some number if you know the concentrations of the reactants. So first part is you need to get the rate law, which we know now how to determine the rate law by doing all those experiments. Once you've done that and you have the rate law, you can predict the reaction rate at any concentration that you decide. So you can make the reaction go fast or slow or intermediate by just choosing the concentrations that give you the rate that you need. So imagine you were trying to, make some product like what's coming to mind now are hand warmers, right? Like if you go out skiing and your hands get cold, you can buy these hand warmers. Let's say you want to invent a new type of hand warmer that uses a specific chemical reaction. How hot that gets and how much heat it gives out per minute will depend on the rate of the chemical reaction going on inside. So if you know what the rate law is, what you could do then is choose concentrations at the start to make the rate whatever you want it to be. Okay, so what we're going to do is take our rate laws and we're going to integrate them. And this will allow us to learn something else, which is it'll tell us exactly what percentage of the reaction is done, like what percent complete is the reaction, I don't know if that's proper English, after some specific amount of time. So for example, if you start a reaction at 1 o'clock and you know the rate law, then you can actually determine what the integrated rate law is. And that'll tell you at 2 o'clock, this reaction will be 70% complete, or maybe it's 90%, or maybe it's 10%. Do I have to leave it overnight? Do I have to leave it for a week? Do I come back after an hour and it's 99%? So I'm done then. This is the sort of information you can get by taking the rate law and integrating it using a little bit of calculus. Now, I think most of you should be in calculus right now, right? I think the traditional way of teaching calculus, at least when I went through, was the first whole semester was like differentiation, doing derivatives. And the second whole semester was integration. Is that still how things are being done? Somebody can tell me in chat. Yeah, pretty much. Okay. So what we're going to be using now is integration, which you won't be having to do the calculus yourself. You can watch what's on the page and you can trust that it's correct. And you can use the product of that, but I won't be asking you to do calculus or to do these derivations yourselves. The integrated rate laws will work differently depending on if the reaction is first order, second order, or whatever. And we're only going to be looking at integrated rate laws for, I would say, the most common reaction examples. These would be zero order reactions, first order reactions, and second order reactions. As we just looked at in the previous example, you can have orders of 2.5. And yes, you can do calculus on that too and arrive at an integrated rate law. But they're kind of rare and we're not going to be looking at them. We're going to be looking at just the common ones. So for a first order reaction, we can say that the rate of the reaction is equal to K times the concentration of A raised to the power of 1. And because it's just a single reactant raised to the power of 1, we can say this reaction is first order. Lots of reactions, both elementary and complex, will have a first order rate law. We also described the rate of the reaction in terms of the disappearance of the reactant. This is what we started our chapter doing. We said that the rate will be equal to the decrease in concentration of A over some time interval dt. And if dt goes to infinitely small, we can say the tangent of that line is equal to the slope is equal to the rate. So what we're doing here basically is just stating two different ways that we can state the rate in terms of either the rate constant times a will be the initial rate, or at that time, the slope of the line, basically at that line. What we're going to do is rearrange it just a little bit. We're going to divide each side by a and multiply each side by gt, which puts it in this form. And then what we can do is integrate dt from 0 to time t. And on the right side, we're going to integrate from initial concentration to some concentration, say AT. And we get something that looks like this. Now, does this look completely alien? Pretty much, yeah, maybe. I guess some of you may have done some calculus in high school, so you may have seen integration already. I don't know if you would have seen much of this yet in this semester, probably not, but that is something you will learn in calculus. When you finish the integration, you end up getting this equation, and all of the equations below that are just different forms of the exact same thing. Basically, they are rearranged forms of the equation that you see on the top. So all of these are really saying the exact same thing. And in my opinion, this is probably the most useful form of the integrated rate law for a first order reaction. So what this is telling you is that the concentration at some time t after the reaction has started will be equal to whatever your initial concentration was times e to the minus kt. The k is the rate constant, and we've seen how to determine the rate constant in this example that we did over here. And t is just how much time. So basically what we can say is if we know what our starting concentration is, and we know our rate constant, then you can just plug in any time t that you want, and it'll tell you a at time t. So if you want to know exactly how much of the starting material is left after an hour, put in 1 hour for t, calculate, and it'll tell you what the concentration remaining is going to be. So this is great for determining sort of, how much of your reaction will be completed after a certain amount of time. And this equation is just directly derived from what we've already learned so far, right in this first line, using just a little bit of calculus. So this is a very, very valuable equation. And notice it's an exponential decay function. So it's e raised to the power of minus kt. So an exponential decay function, I think I have it on the next slide, will look like this, where we start at some initial concentration at A. The rate starts out fast and then slows down. It exponentially decays like that over time, and you can see eventually this plot approaches 0. It turns out that this actual reaction predicts that it actually never reaches 0, that the concentration of reactant never goes to 0. That means the reaction is technically never complete. Although us chemists are very practical, we don't wait for it to be 100% complete. If the reaction is 99% complete, generally speaking, that's good enough for us. Sometimes 95% is good enough too. So we can plug in when the reaction is going to be 99% complete. If you started with a concentration of 1.00 molar and we want it to be 99% complete, what that means is we want our final concentration to be 0.010 molar, right? That means 1% is left, 99% is complete. You can calculate the time that is going to take as long as you know what K is. So this is another application of this particular equation. You can calculate time taken to get to a certain percent completion, or you can calculate percent completion after some given amount of time. Both very useful. So yeah, the plot here is curved. What you will find as you go through physics and chemistry, maybe more and more, especially on the physical side where we're doing measurements and drawing graphs and this sort of thing, people like straight lines. And the real reason why I think people like straight lines is because most human beings are pretty good at drawing a line of best fit with a ruler through a bunch of random data points and calculating slopes that way. And this is how all of these curve fitting was done prior to computers that would do this analysis for you. So there's a linear form of that same equation. Remember our equation for first order is concentration of some reactant at some time t is going to be whatever the initial concentration was times e to the minus kt. What we can do is take the natural log of both sides of that equation, and you end up with this form, that the ln of natural a the t equals minus kt plus ln a0, a naught, which is your initial concentration. This is in the form of y equals mx plus b, where ln a0 is the intercept, k is the slope, and t is your variable time, right? T. This will produce a straight line like you see here. So if you have a chemical reaction and you can follow easily the concentration of A over T, what you can do is take the natural log of A, plot that versus time, and if you get a straight line going down like this, you know that that reaction must be first order. It's not all you know. Because you know the slope is equal to minus K. So you know the slope as well if you can draw a plot like this. So technically you can do the exact same thing, get the exact same information from a curve plot like this, except you can't do that yourself. You can't do this on graph paper and do a fit very easily to a curve. We can do fits on paper to straight lines quite well, but fits to curves like this are very difficult to do. Easy for a computer. The computer doesn't care if you use this equation or the next equation, but I think a lot of people still like to think with straight lines. So basically this equation and this equation are the exact same equation, just take the natural log of both sides. It's like a rearrangement of the same equation. Great, we're doing well. Let's do an example. At 25 degrees Celsius, the rate constant for the first order decomposition of a pesticide solution is that. So a rate constant, remember, is K. K equals 6.40 times 10 to the minus 3 minutes to the minus 1. We can actually tell immediately that this is a first order reaction. It doesn't say so in the question, but we know it's first order because of the unit of the rate constant. We looked at this a little bit last class, but rate constants, if it's first order, will always have units of time to the minus 1. If it was second order, it would be molarity to the minus 1, seconds to the minus 1. So we can tell from the units that this is first order. Isn't it in Star Wars? Don't they call first order, like Kylo Ren and all those guys? Yeah, maybe completely irrelevant here. Okay, starting concentration of pesticide is that number. So starting concentration is A0, 0.0314 molar. What concentration will remain at 62 minutes? So T equals 62 minutes. Notice that the temperature is stated at 25 degrees. It tells you the rate constant, and it wants to know after 25 degrees. This number is not part of our calculations, but it is important to understand that K changes when temperature changes. So only use K if the temperature that K was measured is the same temperature you're doing the reaction at. This doesn't work if we're at 45 degrees Celsius. You can't use the K from 25 degrees Celsius and expect to get the correct answer. It's nice in biochem because almost always it's the same temperature. It's always body temperature, which is like, what, 37 degrees Celsius. But here we're at 25 in both cases, which is like room temperature. That's what we consider that to be. Although to me, I prefer room temperature of like 21 degrees. I find this a little warm, but that's just me. Okay, so we want to know what the remaining amount is after 62 minutes. So the remaining amount is A at time t, which we don't know. So we can use the form of the equation where we have A at time t equals our initial concentration times e to the minus kt. We know all these numbers, 0.3, no, 0.0314 molar times e to the minus k is 6.40 times 10 to the minus 3 minus the minus 1 times 62 min. Right, I have this. Give me 1 second. The answer is 2.11 times 10 to the minus 2 molar. Something I recommend you do, and it's something I always do when I solve an equation like this, is look at the answer and try to like conceptualize, like, what does this mean? Does this make sense? If you screwed up the calculation, it really helps determine if you did or not. That equals as well 0.0211 molar. So notice our initial concentration was 0.0314, and now our concentration is 0.0211. Basically, we've decreased it by a third, right? It's gone down by a third. And think about the application here. Look at what's the question asking. And probably by now you're trained to look at a word problem like this and like filter out the extraneous information. So you don't care, you probably forgot that this is a pesticide solution, or maybe you never even thought, why do we care? You just want to get to the answer. Well, we do care. Pesticide solution, let's say you're going out in the woods and the pesticide solution is to keep ticks off your legs. Is the pesticide solution going to work for you if it decreases by 1/3 after 62 minutes, after 1 hour? You know, so you go outside after an hour, a third of your insecticide is decomposed. Well, maybe that's fine if you're going for a 1 hour walk. Maybe that's not fine if you're going to be working in the woods for 12 hours. These are the sorts of applications to answering these sorts of questions. Or let's say you have pesticide solution and you want to spray it on your crops. Should you mix it up the night before? Well, definitely not if an hour later a third of it is gone, right? This is actually a good thing for pesticides, for them to decompose quickly, because you don't want them to build up in the environment. But in this particular example, it would mean that you'd want to mix it and make the solution immediately before you spray it, so you actually have the pesticide before it's decomposed doing its application that you're asking it to do. All right, I think this is probably a good place to stop. We did quite a bit today, especially conceptually. We're going to apply the same concept of getting these integrated rate laws as well for 0 order and 2nd order. And I'm happy with where things are. Hopefully we can meet in person for those that would like to meet in person on Wednesday's class. I'm still expecting a result. Probably today is my guess, but definitely by Wednesday. I'll be pulling my hair out if it's not. So thank you all, folks, and we will see you before too long.